All right. So what we're going to be doing today is we're going to stay in chapter 2. So this is the big chapter. A lot of things in chapter 2. We just looked at the mean. We learned what it is. We learned how to calculate it. Today we're going to continue on with our journey through chapter 2, and we're going to focus on variance and standard deviation. And then both of those will be used in the final portion of that chapter, calculating z-scores. Z-scores are going to be used, specifically z-scores and things that are like z-scores will be used, especially in inferential psychology. So we're all building towards learning about how to do z-scores, which will use both means and standard deviations. So to that end, what are standard deviations and what is variance? Well, let's set up a situation here where you would want to know about variance, you would want to know about standard deviation. So let's say that you were working in a clinic and you dealt with people with depression, and specifically you had two groups of people under your care. Group A, they had a certain type of depression. Group B, they had another type of depression. And let's say that people that are beyond a certain level of depression, the policy in this clinic is to put them under suicide watch, just to make sure that they don't harm themselves. So you would want to have an idea of how many people in each group you might need to make accommodations for, you might need to have place for in this suicide watch. So again, if it's higher depression that leads to a need for suicide watch, then if you took a look at the means, you might say to yourself, well, Group A, their average depression right now is 42.6 on the Beck's Depression Inventory. Group B, their depression is lower, 25.7. So you might imagine that more people are going to be under suicide watch in Group A than there were in Group B, because on average, their depression scores are higher. However, it can be the case that the two of them have different variance, different variabilities. So it might be that the average for Group B is lower than the average for Group A. And you might think from that there's going to be more people in Group A that are going to fall into this suicide watch criteria beyond this level of depression. However, it all has to do not just with the means, but with also the variance. So if that is the variability of people with depression type A who are in Group A, not very variable, but that is the variability in depression for Group B, you can see that even though Group B has a lower mean, their scores are way more spread out. There's way more variation in the levels of depression for Group B, and it's them and only them that have patients that might fall into that suicide watch category. So we're going to see today about the concept of variance. It's a second number that you can give to really help understand a distribution. So we already found the mean, and we looked at that one last time. That tells you where the center of your distribution is. And now we're going to take a look at a second number, the variance or the standard deviation, and that lets you know how spread out your distribution is. So two numbers can give you a good idea about your distribution and what you're dealing with. All right, so there will be extra practice, but before we get to that, introduction to variability. I will mention its importance to inferential statistics. So when we finally get to start doing the cool stuff about testing psychological data, we're going to be using variability. And then we're going to learn how to calculate the standard deviation and variance for a population. This is what you're going to be using for your homework and for your post-test and pre-test at this point when you're doing variance and standard deviation. However, it's technically wrong. And I don't like to start teaching things that are technically wrong. So we're also going to introduce the idea of standard deviation and variance for samples. And I'll tell you when we're going to be using that. Mostly that's going to be used for the exam, and it's the correct one to use. So there's one for population, one for samples. That'll make more sense as we look at it. And then finally we'll have some time. We'll go through an in-class practice. I'll mention the homework assignment, and then we'll have extra practice time at the end of class. All right, so what is variability? So take a look at the following frequency distribution. Hopefully by now, frequency graphs are getting pretty automatic. So we have our possible scores right there. We don't have the axis saying it, but that's a frequency on the y-axis. And again, this is like a massive apartment building. where the height of the line indicates how many people are living in each location on that apartment building. So that frequency distribution has a mean of mu, so that is a population mean. So the population mean is right there. It has a mean of 100. So that's one distribution. This second distribution, completely different distribution, also has a population mean of 100. So distributions that have the same mean can vary widely, and that varying is that variability. So some distributions can be really wide, meaning that the scores in that distribution have a wide range of values. You see we go anywhere from 60 all the way up to 140 for this set of scores. But for another set of scores, maybe not such a wide range of values. These ones only go from 90 to 110. Same mean in each case, same population mean. So when we're describing a distribution, when we want to give a one number that describes a distribution, oftentimes we give the mean, and then to that mean we add a measure of variability. So variability is what we're focusing on. It's a quantitative measure of the differences between scores in a distribution. So it's all well and good if you're talking informally about a distribution that's really wide, about a distribution that's really narrow. But at some point to do the science, you got to put numbers on it so that we can communicate with other people and know exactly how wide or how narrow it is. So that's what variability is. It's a number that tells you how wide a distribution is. What is the difference between different scores in a distribution? Another way to think about it is how spread out are the scores. If they're really spread out, a lot of people are scoring very differently on this particular score. If they're really narrow, a lot of people are scoring, much the same. So something like weight would be widely distributed because you have people from both ends of the spectrum. Something like what planet do you live on would be very narrowly distributed because everybody's on Earth. And you'd have a little bit of variability for the people in the space station, but that's it, right? So for some scores, wide variability, very different. Other scores, very narrow. All right, the importance of this concept of variability to inferential statistics comes from the fact that when we get to inferential statistics, we're going to be looking at strategies and procedures. And basically what it all boils down to is there a difference between two populations? And basically what that boils down to is whether or not their means are different and whether or not they're not very spread out. So when we take a look at inferential statistics, let's say that we take samples from these populations. So we're always interested in a population. We're always interested in everybody dealing with depression. How can we treat them? We're always interested in everybody using social media. What effects does it have on their behavior? But we never get to test everyone. So we take a sample from each population, and we might have sample A, and we might have sample B from a different population, and we want to know, are they really different? Right? So this might be instant gratification scores, and this might be people who don't spend a lot of time on social media, and this might be people who do spend a lot of time on social media. Is there a real difference in their scores on a measure of instant gratification? Well, what inferential statistics will do is they'll take a look at the distance between those two means of the samples, and it'll make a determination as to whether or not this represents a real difference. And that gets harder the closer those means are. So the more overlap there is, the less certain you can be that that small little difference between the means of these samples actually represents a real difference between these populations. However, means are not the only thing inferential statistics takes a look at. It also takes a look at the variability. So as those samples become less and less and less variable, you can see that once again they're split, they're separate. So inferential statistics takes a look at the mean difference. Inferential statistics takes a look at the variability of the samples. And in this case, it would say, yes, there really is a difference, because even though they're really close, notice they barely overlap each other. Whereas here, inferential statistics would say, probably not a real difference between these two populations, because they're super close and they're super overlapping. So that's just your kind of foreshadowing to inferential statistics. Takes into account both the mean and the variability when making a decision if there's a real difference between two populations. All right, so what we're going to do now is we're going to start with our look at standard deviation and variance for a population. We're going to start with the population because that's the easier one to calculate. That's the one that your book starts with. But just as a spoiler alert, in your entire psychology career or whatever field you choose, unless you're working for the US Census, you'll never have access to population data. You never have everyone. So you're going to be calculating population, standard deviation, and variance in this class, and probably never again. But it's the easier one to start with, so that's why we're going to start with it. That's why your textbook starts with it as well. All right, so that's the population distribution. There's your population mean. First concept we need is the idea of deviation. And what deviation is deviation is nothing more than your distance from the mean. So every single score, every single individual that makes up this distribution has a certain deviation, has a certain distance that their score is from that calculated mean. So this guy right here, that X score, that is a positive deviation. It's kind of close to the mean, but that distance between that score and the mean, that's the deviation. This one has a slightly negative deviation, right? It's below the mean. This score down here has a large negative deviation. It's way below the mean. It's way far away from the mean. This one has a large positive deviation. Some scores will have 0 deviation. So if your score is the same as the mean, then there's 0 deviation. So again, it's the distance of every score, or any single score, is the distance from that score to the mean. And we represent it simply as the score minus the mean. So if you ever want to calculate the deviation of a score, find the mean for the distribution, take that score, subtract away from it the mean. There you have its deviation. Now, one good way to express variability is to just take these deviations and find your typical, maybe your average deviation, right? Because if your distribution is very spread out, then your average deviation is going to be, well, it's going to be bigger. But if your distribution is squeezed together, then your deviations are going to be smaller. The problem with that is because the mean is the balance point for this distribution. These deviations on this side, when you add them to these deviations on this side, it exactly cancels out to 0. And that does not work in terms of trying to get a numerical value for how spread out things are. So for reasons that are way beyond the scope of this course, and probably way beyond like grad school stats, statisticians decided that the way that they're going to get rid of these negative values, these negative deviations, is they're just going to square everything. So positive 3 squared equals 9, negative 3 squared equals 9. So all of these deviations got squared, and we have our next concept, which is squared deviation. All right, so squared deviation is literally what it says. It's the distance from the mean squared. So we have that in parentheses, the score minus the population mean, that is your deviation. And then you take that number and you square it, and you get rid of all your negatives. So that's the next step towards variance and standard deviation. We take all the deviations, we square them all, we have now squared deviations. The next step, we are going to add them all together. So remember I told you statisticians love adding things together. It's almost a first move in so many calculations. We're going to sum these squared deviations. We are going to summation, the distance from the mean, the deviation, all of that squared. So remember, distance first, squared second, and then we sum it. We got to do order of operations. So it's the deviations squared, and then you take all those deviations and you sum it up. Now, this is so incredibly important, occurs so often that statisticians gave it an abbreviation, and they abbreviated the abbreviation. So prior to the advent of modern computing, statistics in universities was mostly done by locking grad schools in towers and giving them stacks of data and telling them they can get out when their job is done. Thankfully, I wasn't around those days. But anyways, these grad students, remember, pencil and paper. They were doing all of this by pencil and paper. So they were sitting there and they were like, all right, sum of squared, deviations. And they had to write that again and again and again. And these poor grad students started getting carpal tunnel syndrome. And they said to themselves, you know what, how about we abbreviate this? SSD, sum of squared deviations. That's great. And they were writing this out and writing this out. This is used so often in statistics, and you're going to see this in inferential statistics all over the place, that they got carpal tunnel syndrome writing out SSD. So they said, can we all just agree, SS, let's drop the D, let's save ourselves 33% of writing. I made that story up, but that's basically just an indication of how important this is. They didn't even want to write the D, they used it so often. So unfortunately, the burden of knowing what this is has fallen to you. Because you will see this written, you will see this read, you will see this referred to as sum of squares. And this is my public service announcement. Be very, very careful, because the one thing that this is not is the sum of squares. This is the sum of squared deviations. So whenever you see SS, read it as the sum of squared deviations. From here on out, when you're reading about sum of squares, read that as sum of squared deviations, because the sum of squares is the sum of squares, right? You take your scores, you square them, those are the squares, you sum them up. That's what the sum of squares is. That is not sum of squared deviations. So those poor grad students just couldn't take it anymore, and they called it the sum of squares. So now it's up to us to honor their memory and remember sum of squared deviations. So again, when you see any of this, don't read it out as a symbol, but especially when you see SS, not sum of squares, read it out, sum of squared deviations, and hopefully you won't fall into that trap right there. All right, so we have the sum of squares, sum of squared deviations. That's the definitional formula, the sum of squared deviations. So there's a definitional formula. I'm going to mention the computational formula just so that you're not confused. That formula is mathematically equivalent to that formula, but this one is a whole lot easier to calculate by pencil and paper. So if you're ever trapped on a desert island and you have to do some stats, you're going to use that formula right there. But for us, the definitional formula gives us an understanding, the sum of the squared deviations, that's what it is. And in terms of calculating it, we're going to use Excel anyway, and we're going to see more on that later. So when you read about computational formulas in your textbook, they're exactly what you just read about. It's just mathematically easier to calculate. All right, so we took these deviations. We squared these deviations. We summed up these deviations. Now we want to find out the average squared deviation, and that's where we get the population variance. So population variance is the mean squared deviation. You have all these squared deviations. What's the average? What's the mean? So it's literally just the sum of the squared deviations divided by the number of scores. So you take your sum of squared deviations, you divide that by the number, you find the average squared deviation, and that is given sigma squared. And again, read that as population variance. So populations, their terms are the Greek symbols, and this is the one for variance, and you'll see why it's squared in just a little bit. But sigma squared, that's the symbol for population variance. All right, so we have sum of squared deviations divided by the number of scores. That is your population variance. Directly related to that is population standard deviation. So what we have here is not the average deviation. It's the average squared deviation. It's like if somebody asked you what's your GPA and you told them, oh, well, my squared GPA is 12.57. They don't want your squared GPA, right? They want your GPA. So same thing here. We don't want a squared deviation, an average squared deviation. We want a standard deviation, like a regular deviation. So all we do is we take that population variance, we take the square root of it, and we end up with population standard deviation, and that's the one that gets the symbol sigma. So population standard deviation gets sigma, population variance, sigma squared. If you have the standard deviation, you square it, you get the variance. If you got the variance, you take the square root, you got the standard deviation. They're locked into one another by that relationship. All right, and those are the two standard measures for the spread, the variability in a population. Any questions so far on that? All right. So I mentioned that the population one was easier to kind of introduce the idea of variability. So now we're going to take a look at the standard deviation and variance for samples, because we need to make a slight adjustment. It's the same idea, but we need to make a slight adjustment. So I'm going to teach it to you now. This is how we're going to be doing it on the exam. I'll show you how to calculate population variance and standard deviation today as well. But for the exam, because we're going to be doing it the right way, we're going to be using variance and standard deviation for samples. And the reason we need to have a slightly different formula, a slightly different concept for this, is that samples, they tend to be less variable than a population. So this is just what happens. This is just the way it works out. So if you have your population right here, and you take a sample out of that population, you grab 5 scores out of that population, and they have certain variability. The population variability takes into account the entire spread of the population. So you can think of this as your entire population variability. And unless you are incredibly lucky and you choose that one extreme person living at the maximum of these population scores, and you also choose this one extreme person living at the minimum of the population scores, unless you get those two people, your sample variability is always going to be less than your population variability. Just the way that it shakes out. So this is an issue because we want to use the sample to estimate populations. That's why we look at samples. What's going on with these 30 people? Let's use the information we have about them to estimate what's going on with the population of millions. So we want to be able to estimate population variance from sample variance. So we need to adjust the formula for sample to calculate sample variance just a little bit. So we need to make it bigger, and we've probably all done this in other areas of our lives. So you probably know somebody in your circle of friends who never knows how long it takes them to get ready. So you're trying to make plans for Friday night, and either you know a friend like this or you're the friend, but you call them up, you're like, man, I'm on my way. How much longer, do you need to be ready? And they're like, oh yeah, 20 minutes. I'll be at the door in 20 minutes. And you know that that's not true. But you also know that it's not useless to call this individual, right? It gives you information. So you know that her 20 minutes means 30 minutes. So you say, all right, great, I'll see you in 20 minutes. And then 30 minutes later, you show up at the door. So it's the same thing with population variance and sample variance. We know that sample variance is underestimating its variability. So we get that information, and then we just do a little correction. So 60 minutes means 90 minutes. 10 minutes means 15 minutes. It's not useless information that we're getting from the sample variance. We just need to correct it so it's actually representing the truth of what's going on in the population. So what we're going to do is we're going to take a look at that correction and take a look at the formula for sample variance, and then we'll start calculating these out in Excel. All right, so the first concept we need for sample variability or sample variance is deviation. Same idea as a population. It's distance from the mean. It's the score minus the mean for the sample. So that's the first concept. That is exactly the same as what we just saw for the population. Once again, if you just added those all up and took the average, you will get 0 every single time. So we got to take those deviations, we got to square them. So we have squared deviation, distance from the mean, all squared. Your score minus the sample mean, and you square that. Again, analogous to what we saw with populations. Next, we got to start finding the average of these squared deviations. So we add them all up, sum of squared deviations, the sum of the distances from the mean squared. So once again, we have the deviation, you square it, and then you add to that, or you square it, and then you sum up those squares. Once again, those poor grad students have to write that out a bajillion times, so they abbreviate it right down to SS. SS stands for sum of squared deviations, but you'll see people talking about sum of squares. You'll read sum of squares. Do not read sum of squares in your own mind. Do not read sum of squares when you talk about it out loud. And I will continue to refer to this as sum of squared deviations because, again, that is the sum of squares, and this is not that. So we've got to be very clear. We're looking at the sum of squared deviations. So we take that sum of squares, and much like in the population, there's that definitional formula. Much like for the population, if you're ever stuck on a desert island, there's your computational formula. And even more so than for population, we're going to be using Excel to calculate the sum of squared deviations and variance and standard deviation for samples. However, when we want to calculate sample variance, if we want to do by hand, if we want to see what's going on behind the curtain, we need to correct it a little bit. So it's the mean squared deviation. But because samples tend to be less variable, what we need to do is we need to take that sum of squared deviations and we need to divide it by the sample size minus 1. And that minus 1, I told you minus 1s are all over stats. That minus 1 makes that final answer a little bit bigger. So we have our sum of squared deviations divided by the size of your sample minus 1. So just to kind of illustrate, if you had a sum of squared deviations that was equal to 90, and you had a sample that was of size 10, without the correction, you'd have 90 divided by 10. That would give you a variance of 9. With the correction, you have 90 divided by 10 minus 1. That's 90 divided by 9. And you can see that you get a bigger number. That's the correction. So that minus 1 is just a way of correcting the fact that samples tend to be less variable than their populations. So that variance that we just calculated, that has the symbol S squared. So S is for sample variance. Read it as sample variance. And then this is directly connected to sample standard deviation. So the same way that sigma squared was population variance, sigma was population standard deviation. S squared is sample variance. And you just take the square root of that and you get S, which is sample standard deviation. All right, so that is the new concepts that I wanted to introduce here. So we now kind of know what variability is, sample variability and population variability. So let's start practicing on that. So we're going to go through some in-class calculations. So if you haven't already, please open up 06 practice. That's for September 6th, not extra practice, but the regular practice. And I will stop the integrity recording. All right, so the sheet that we're looking for is that guy right there. So we are going to start up on our first example here. Let me zoom in. Whoops. Zoom to selection. All right, so once again, we got 3 sets of scores. We got a set of X scores right there, set of Y scores right there, and then finally a set of Z scores. So again, we measured subjects on 3 different surveys, got 3 different sets of scores. And now we want to know the sum of squared deviations, the sample variance, and the sample standard deviation. So we're going to talk about mostly how to do sample standard deviation, sample variance here. I'm going to show you how to do population though, so you can use it for your homework and any upcoming pre-tests or post-tests. So what we're going to do first is we're going to start off with the sum of squared deviations. So we go down to this cell here so we can put in our formula. We type in equals. That lets Excel know that we're giving it a formula. And I'll show you first what not to do. So if you put sum SQ, like sum of squares, there is a formula there, and it will say, hey, this returns the sum of the squares of the arguments. If you're continually referring to SS as sum of squares, sum of squares, sum of squares, sum of squares, you make yourself vulnerable to falling for that trap. That is not the formula you want. That is the wrong one. We want sum of squared deviations. So for that one, it's DEV SQ. And again, if you read the description, Excel is very nice. It gives you these little descriptions. Returns the sum of squares of deviations of data points from their sample mean. That is literally the dictionary definition of sum of squares deviations. That's the one we want. So we open our parentheses, highlight the scores, close those parentheses, hit enter. And sum of squared deviations is always going to be a huge nasty number. So when you get something like 10,293.67, don't panic. That's what it should be. We pop it into the answer cell, and we see that we got that one correct. Incidentally, my Excel auto-corrected the width of the column. Just to kind of show you what might happen. If this ever happens, hashtags is the message that Excel gives you. What this means is that your number's in there, but it just doesn't have the space to display it. So an easy way to fix that is to just go up to the top here, go in between the 2 columns, and when you see that little double-sided arrow, if you click and you just kind of move it to the side of it, you can open up your columns. If it happens during an exam, call me over and I'll just, real quick take care of it. All right, so we got the sum of squares. Let's do that one more time. If you want to practice your copy and paste, feel free. But just so you see it a few times, equals DEV SQ, sum of squared deviations, open parentheses, we'll highlight those cells with the scores, close parentheses, we hit enter. And then finally for the Z-score, DEV SQ, open parentheses, highlight the scores. For the Z-scores, close those parentheses, we hit enter. A massive number, over 63,000. Pop those into our answer cells, and we get those 3. Whoops. Correct. Oh, and look, the Z one didn't update. So again, we can just make that column a little bigger. So the hashtags means that your number is there. It just can't display it. All right, so next thing we're going to calculate is sample variance. So I'll show you sample variance. I'll show you very quickly population variance. They're both pretty straightforward. So we put in equals to let Excel know that we have a formula coming up. We type in var, and anytime that there's a difference between a population calculation and a sample calculation, Excel will have these little .p's and .s's. So .p is when you calculate the variance for the entire population. So that's when you're dealing with population data. .s is when you're dealing with sample data. So you can use .p and .s when you're calculating for a population, use .p. So for example, your post-test, your homework coming up, use .p. .s, you can use that for when we need a sample. And I'll be very clear on the exam. I'll remind you again, we're just doing sample variance, sample standard deviation. But just to kind of show you how often samples are calculated, sample variance is calculated. If you take a look down here at just var, right? Just var for variance. You'll notice that it is variance based on the sample. So the default for Excel is the thing that everybody uses, and the default for variance is based on a sample. So if you want to use .s, feel free. If you want to just use var for samples, feel free. I'm going to try .s just to keep it all clear. So we put var.s for a sample. Open those parentheses, highlight your cells, close those parentheses. We hit enter. That's the variability. Definitely don't want to enter that in manually, so we put it into our answer cell using the equals function, and we got that one correct. So, bless you. So, again, equals var.p if it's a population. In this case, we're going for sample variance. So we do .s, open those parentheses, highlight those cells, highlight the scores, close those parentheses, hit enter. We have our sample variance for the y-scores. Let's do it one more time. Equals var.s, open those parentheses, highlight those z-scores, close those parentheses, and we have the variability for z, and we pop those into our answer cells, and we have the variance, sample variance for x, y, and z. So notice that in terms of the variance, what is being told to us with these numbers is that z is the most spread out. It's the most spread out scores, and you can see that because z goes all the way down to 4, all the way up to 263. So now we have a numerical estimate of how spread out z is. You can see that y is much less spread out. And again, if you take a look at its scores, the y-scores are much closer together. They go from a low of 14 up to a high of 156. Nowhere near as much spread as the z-scores. And the x-scores have the least amount of variability. And you can see they have a low of 5, only a high of 90, and most of the scores, sorry, high 91. And most of the scores are pretty close to each other. And again, that's numerically calculated in that score for variance. All right, and the last thing we need to do now is we need to calculate the standard deviation. And the standard deviation, much like the variance, very friendly. So we have two friendly formulas, one for variance, one for standard deviation, one horribly unfriendly formula for standard for deviation, sum of squared deviations. So sum of squared deviations, DEV-SQ, var variance, very friendly, var.s. Standard deviation equals STDEV, also very friendly. Standard deviation, and once again, you'll notice that there's a difference between populations and samples, so that's reflected in Excel. So if we wanted to do this for a population, we'd go .p. We're going to do it for a sample, so we go STDEV.s for sample. Open those parentheses, highlight those cells, close them up. And you can see that the standard deviation that we have is the square root of the variance. So if you take that 30.59 and you square it, you're going to get 935. That's just a relationship between the two. But, you know, we use the pre-built-in formulas because it's super easy. Put it into the answer cell, and we get that one correct. So two more times equals STDEV.S for sample. Open parentheses, highlight those cells, close up those parentheses. We have the standard deviation for the y-scores. And then finally, sample standard deviation, STDEV.S for sample. Again, it's .p if you're doing a population. So once more for your homework, use the .p's, highlight those scores, close your parentheses, and we have the standard deviation for the z-scores. Pop those into our answer cells using that equals function, especially important now because the whole numbers are gone, and you get all of those correct. All right, so was everybody able to get 100% on this? All right, so we have a few more examples here, so you can practice your formulas, practice your copy and paste. All right, so hopefully you've had a chance to try that out with the previous one for means, medians, and means. Try it again over here. The more comfortable you get with cut and paste, the quicker you can do things. So there's a few more examples here for sum of squared deviations, sample variance, and sample standard deviation. And I'm just going to do a quick little wrap up, and then we will turn the rest of the class over to practice time. All right. So just to wrap up today's class, you now have formulas for sum of squared deviations, variance, and standard deviation. Remember, .p for a population, .s for a sample. So when you're doing your homework, when you're doing your pre-tests, be very careful. Make sure that you look for that information, because they will tell you, oh, this is data from a population. Or they will tell you, oh, this is data from a sample. So look for those words. 9 times out of 10, though, at this point in your homework, it's going to be population. All right, so for the quiz me options, for the study plans, I've had some questions. There seems to be a little bit of confusion. I guess it's not very clear in the feedback that you're getting from my lab whether you have completed all of your quiz me requirements. So what I'm going to do is either tonight if I have a chance, but definitely by the end of tomorrow, I'm going to update your pretest 1 and pretest 2 scores, and I'm going to do in that correction. So I'm going to take the maximum for your pretest 1 score, or what you have completed in the study plan by the time that I get to it, again, probably tomorrow. I'm going to post that to Canvas, and that's going to kind of let you know where you're at. So if you're thinking, oh, maybe I've done 100%, but I'm not sure of the study plan, I'll post your grades, double check it. If you have 100%, that means you finished 100% of the study plan. If it's less than that, that means that you're missing something. So this is just to sort of, help everybody figure out whether they're doing the actual complete quiz me's. And then, so I'll do that, again, by the end of Friday. I'll probably get to it earlier. But then the actual due date to earn these 100% are going to be by the exams that these pretests are trying to get you ready for. So the actual time that you have to finish the study plan quiz me to get 100% on these pretests is by exam number 1. All right, so that's the due date and after exam number 1, whatever you have is going to be the grade that you get assigned. All right, so I'll be doing that again sometime tomorrow. So double check, if you have any questions. Oh, I think I finished 100% of the study plan. If you don't have 100% on your pretest, post it in Canvas again by the end of Friday. You're missing a little something. Other than that, we got like half an hour left in today's class. That's all going to be for practice. So extra practice, there's another Excel sheet just so you can continue practicing these formulas, continue practicing these copy and paste. You also are now ready to tackle your homework assignment number 4, chapter 2, part 2. I mentioned I got some emails from some students that number 5 was not available. It will be available. I'm going to take a look into that, but definitely you can start on your homework assignment number 4, and it's going to be doing some variance, doing some standard deviation. Mostly it's going to be populations though. So again, use Excel, but you're going to be going var.p, and you're going to be doing stdev.p as well. And that is, yes. I was wondering why I have that duplicated. Basically, fun little zoom graphic for things that I just mentioned. Use population variance and population deviation for your homework. Other than that, that's all that I wanted to cover for today. So we got half an hour that we can dedicate to practice time. So give these new concepts a shot. Go back and revisit old Excel sheets if you haven't finished those up yet. Check your homework, check your post-test. Do these questions. Call me over if you need any assistance. Or if it's been a long week, feel free to call it an early Thursday. And yeah, but otherwise, call me over and I will give you a hand.